Aris Georgiakakos from Georgia Tech with Decision Science, Nick Graham from HRC and Scripps Institution of Oceanography with Climate Science, Joe Hagan, who managed quite a bit of this work at the Energy Commission, and Dan Cahan have contributed with comments and suggestions and helped me shape this talk. So the presentation focus is reservoir management in Northern California under climatic variability and change. Essentially, I'll be talking about the set of reservoirs, large reservoirs in Northern California that essentially store the snowmelt and rain-fed flows from the upstream basins and then make deliveries to downstream users who then support the trillion-dollar economy of California. I'm going to give you a little bit of background. I'm not sure how many people are familiar with these concepts, but a system of reservoirs modulates the climate and weather variability in order to produce downstream benefits. So extremes are not something new for reservoir management. In fact, that's the reason the reservoirs are there, is to modulate that variability. And the downstream benefits range from flood damage mitigation, hydroelectric power production, water conservation for municipal, industrial, and agricultural supply, ecosystem benefits, and others, recreation, so on. As you may think, reservoir effectiveness is substantially influenced by climatic variability and trends, the demand variability and trends, sometimes more so than the climatic variability and trends, previous speakers mentioned that, and changing water markets. An important target of reservoir management is to maximize water use efficiency, essentially. So some of the elements of current reservoir management in California, essentially simulation runs with historical data and statistics, a detailed numerical description of the system. Both are used to get a set of what are called guide rules or operation rules on which to base operational management. So these rules then protect the downstream areas from flooding. They try to maximize the water benefits for downstream users and so on. In some cases, these rules are indexed by climatic variables, such as, for instance, observed precipitation. In California, there is no use of forecasts for management, but just observed precipitation that's on the ground. And an example of that is from flood management, where you can see here from a paper by Willis and co-authors, a recent one, you can see the Oroville rule curve that essentially describes, this is a line, it's actually a set of lines, but if you focus in one of them, essentially it describes the maximum storage or reservoir level that is allowed so that there is enough storage for flood control left over. And the rule curve started about mid-September, and there's a drawdown period down to about mid-October. Then there is a flat line which maintains itself to allow flood storage during the flood season, and at the end of March, beginning of April, we have the filling curve that essentially brings the water level high so that the summer uses can be maintained and sustained. Now, the different curves now are indexed in a discrete fashion by a observed precipitation index that is used to determine whether this is a dry year or a wet year and so on. Now, planning involves several stakeholders and several objectives, as well as some coordination among reservoir sites. You can imagine that's a complex process that's going on. It's important to note that no two systems are the same, and generalization is difficult in reservoir management, particularly because of the situation with climate. You might be in a regime where you have a mix of rain and rain-fed flows and snow melt, and you might be in a regime where you have snow melt primarily. These are two different regimes that would affect substantially how you would manage your reservoirs. Demands might be different in different places, and of course system structure might be different. How many reservoirs, how they're connected, and so on. An important other issue that I think was alluded to by previous speakers too is that climate and weather predictions must be translated to system decision variables to be useful for management. An example might be this recent paper by Huang and others essentially concerning the salmonid fisheries management, cold water species. And you can see that essentially climate and weather prediction will provide information on surface temperature, wind, a certain set of transformations would happen, and then these variables will be transformed to water temperature released from the reservoir, which essentially is a decision variable index. So we're not directly using this. We're making that transformation to use that in our decisions. And sometimes it happens both here in the US and elsewhere that we think that by providing an ensemble of equally likely predictions of a climate event or a weather event would be sufficient for management. In many cases, that's not the case. We need to make that transformation so that managers can use what they're really calibrated to use. So I'll discuss two issues. The first issue is the Integrated Forecast and Management Project. We call it INFORM for Northern California. This is a prototype demonstration project that is been going on now for 10 years in collaboration with forecast and management agencies in California. And secondly, an assessment of adaptive reservoir management versus current management practices through simulation experiments. And you can see links to both those in articles that are about to appear. So the INFORM region is the Northern California region, and you can see there some of the major reservoirs there. We're talking about capacities order of from about 1 billion cubic meters to about 5.5 billion cubic meters. And these reservoirs are connected in various ways through mass balance and energy and other ways. And the vision for this project was to improve water resources management using climate, hydrologic, and decision science. The challenge is shown here, where the deliveries from the reservoir system for 2006, 2007, and 2008 are shown, where about in 2008 we almost have half the deliveries that we had in 2006. The sponsors and collaborators are shown here. These are the sponsors, CalFed, funded initial years of the project. The California Energy Commission continued funding this project from its inception. Thank you, Joe O'Hagan and Guido Franco on this. And then the National Oceanic and Atmospheric Administration as well, Dr. Koblinski and Dr. Carter, Climate Project Office and Office of Hydrologic Development. We form an oversight and implementation committee. You realize that a project like this cannot be done as a desk study. This is a demonstration study. And in that committee, there is a number of representatives from these agencies that are going on. The Hydrologic Research Center and the Georgia Institute of Technology, the Georgia Water Resources Institute, are participating as the decision lead and the hydrometeorological forecast leads as well in this. The INFORM goals and objectives implement an integrated forecast management system for the Northern California reservoirs using real-time data and operational forecast models. So this is not a study introducing new models. We just want to be linked to the operational models to the degree possible, so that we can actually demonstrate differences between what's going on now and what might be going on using a different system that utilizes hydroclimatic forecasts. It's important to note that aspects of the actual system to be represented were selected in collaboration with several agencies. The California system is a fantastically complex system. In this kind of a demonstration project, we cannot implement all the details, but we collaborated closely with the agencies I showed before to identify the major system elements included. The second objective was to perform tests with actual data and with management input over a number of years. It's been now about 10. And then to demonstrate the utility of climate and hydrologic forecasts for water resources management in Northern California for several years. You see here the cartoon that shows the type of intercomparison we're doing. This is the actual system with operation rules, as I mentioned, receives real-time information, input, and system characteristics, and interacts with the decision maker to provide measurable benefits and possibly other benefits, not measurable. The virtual system that we built also uses the same information, except instead of operating rules here, uses risk-based trade-offs. So this is adaptable decision measures. And the decision manager then makes decisions, looks at these risk-based trade-offs between, say, flood control and energy production or water conservation. And once they make decisions, then release policies are developed, and then measurable benefits are obtained. Very quickly, some of the system components. We're linked in real time with the National Centers of Environmental Prediction, so we're receiving the information from them on a daily basis. This information is downscaled. That term was used before. It means that we take the upper air information that comes from these large-scale models and essentially downscale it down to about 10 by 10 kilometer scales throughout this domain. And this information then, in the form of equally likely scenarios produced by these national agencies, are feeding hydrologic models, which then create ensemble inflows or forecasts of equally likely scenarios for the decision component. A very important link is that these models are similar to those run by the forecasters at the National Weather Service in Sacramento, and they're updated daily. Their states are updated daily, so they're aligned to what the simulations and forecasts are of the California Nevada River Forecast Center. The forecasts then are linked to the decision model. Essentially, this is a risk-based trade-off type of model. It doesn't make decisions. It provides trade-offs at given reliability levels to managers. This information is transmitted there. Decisions are made by these managers that develop the release schedules, and then these release rules go into an assessment system that just quantifies the management benefits. You can see here the complexity of the system in its abstracted form that is used in the INFORM component. Very quickly, you can see three lines here, three columns rather, vertical columns. These are forecasts that are generated by the National Centers of Environmental Prediction. This is the so-called global forecast system, which we use for the period 0 to 16 days. This is the climate forecast system, which we use for the period from the period 0 to 35 days. And then again, the same system, but in a different way, we use it out to 9 months. so that in real time we have predictions, and those are ensemble predictions of equally likely scenarios that go from 6 hours essentially out to 9 months. There are various ways that we use these. These two use dynamic downscaling. They use models. This one uses probabilistic downscaling, and there are coupled links so that the models are all consistent and you don't see abrupt changes anywhere. The output of these hydrologic models then is the input to the decision model. The decision model similarly treats all the scales, treats the short time scale, near real time, the mid to short range decision support out to a month. This is out to a day. This is out to a month. This is the resolution. And then the long range decision support 1 to 2 years with that resolution. Then there is a scenario policy assessment with, that goes out to several decades with a monthly resolution. The system is then fully coupled, a two-way coupling. High resolution information is used to provide benefit impact functions for low resolution information, which in turn conditions the high resolution decisions. So decisions are made at the higher level, conditioned on that decisions are made at the lower level, and then finally at the very high resolution level. We use then the corresponding forecast that I mentioned before in the appropriate times and outcome trade-offs, either management or planning trade-offs. This is a catalyst. This system may be thought as a catalyst that links the climate and hydrology forecasts and the forecast agencies to the planning and management agencies in Northern California. I'll show you an example of a demonstration that we did for years 2006, 2007, and 2008. Just using the long-range management model, this is the 1 to 2 years with a weekly to 10-day resolution. I put this here to remind you again that in terms of decision variables, what is important for water managers is the level of these of the various reservoirs, and not necessarily the initial the input that comes in as precipitation and temperature. And so the idea then that this adaptive system is based on is to try to manage the uncertainty, the resultant uncertainty, into these decision variables rather than the uncertainty in the input. It's a critical point, I think, that must come across because many, many systems use the same idea. So here is the 2006, 2007, and 2008. The black bars here indicate the historical averages, and the red, green, and blue indicate the forecast, the 9-month forecast for 6, 7, and 8. So 2006 was a wet year, an average year, and a dry year for 2008, particularly for Shasta and Oroville, these two large reservoirs. I'll show you some results from our demonstration. This is the initial storage, 1st of March. This is the blue bars. And a useful variable to measure performance is the final storage at the end of the season, of the year. And that is the green lines represent the actual storage using current operation rules, and the this color here, the reddish color, is the final storage when we use the adaptive decision support rules. All use the same input, and what you can see is that in the transition year, where we had in the previous year abundant moisture, and we're used with a certain we're using a certain kind of response from the actual system. We seem to have a persistence that goes into this second year, the 2007 year, whereby now we don't get as much water as we thought we were going to get, and now the actual final storage is much less than it could be if we had used the forecast, the climate forecast for this year. Again, these are all commensurate measures, and they were, the decision horizon was from 1 March to 1 March plus 9 months. Okay, so another study funded by the Energy Commission is to use this INFORM system to look at the future through simulation experiments. And to make a rather long story short, because Dan showed me 3 minutes, I'll just go to the results. Essentially what I show you here is basically a comparison between current and adaptive management policies that INFORM advocates for the present and the future. And future here means 2050 to 2099. So what you can see is that the black line, which is the current policies, in a diagram of exceedance probability versus the deliveries, essentially drops substantially for the years that we had drought, essentially in California. So the minimum deliveries are quite low compared to an adaptive policy, even for the current year. However, when you go into the future, then you see that the minimum deliveries dropped even further, while the adaptive policy maintains a uniform response throughout the exceedance probability range. Down here is another way of looking at some of the results, but now indicating different performance criteria. This is the average annual spillage that has to do with floods. This is the average water supply deliveries. These are the minimum water supply deliveries, average energy, firm energy, and the X2 location, which is a measure of the seawater intrusion and violation of the saline water standards in the bay. And so what we see essentially is that particularly in the future climate, but in some cases even in the present climate, the adaptive policy helps us manage the extremes quite a bit better than the current policy. So integrated forecast and reservoir management demonstrates significant capability for mitigating water resources impact of climate and weather variability and uncertainty, particularly for extremes. I would like to just discuss one institutional issue, and I'll stop there. And that is this. Dan asked me, what would you say about the institutional issues for using INFORM in Northern California? Okay, so here's one fact, is that management processes are legally institutionally vested in traditional procedures and are change resistant. I think most water managers would agree with that. There is now, however, collocation of main forecast and management agencies in Sacramento, and there is coordination going on, but that coordination is essentially limited to flood management. There is less and needs improvement for normal dry hydrologic periods. It's not accompanied, this coordination is not accompanied by integrative adaptive tools that encompass the applicable range of timescale sectors and particularly prediction uncertainty. And there is an unintended consequence of this fact, is that it discourages the use of key scientific advances, hydroclimatic forecasting, multi-reservoir optimization, uncertainty characterization, and integrated water resources management. We believe that the INFORM approach, perhaps not the specific models that we use for these examples, but the approach of adaptive management is designed to support a truly coordinated, interactive, an adaptive decision process that consistently reconciles these long, mid, and short-term operational objectives and decisions. And I think this can, in the question, what are some of the issues of using INFORM, or the approach, is I believe if the institutional and legal processes concern themselves with establishing the framework, broad objectives and criteria for shared water management, and not with laying down policy specifics, as in many cases are doing now. I think if that's the case, then we can move ahead. And with agency coordination, the approach, this INFORM approach, may become institutional practice as a real-time screening and planning tool for identifying beneficiary release policies. Of course, once that is designed and promising policies are identified, then the detailed simulation tools that we have in California that look at the exact and actual system can take over and refine these policies and develop, in fact, operational decisions. Thank you.